Hello everyone. Originally, I was going to do a video on cosmology where I talk about the Friedmann equations, multi-component universes, and the evolution of the universe. But then I realized that I could have done that video better and talked about the evolution of the universe in a more enlightening manner, where I show you more qualitative pictures using phase portrait analysis. So I'm still generating the phase portraits in Mathematica, and as a result, that video is pending, and I will release it maybe in 2 or 3 days. So instead, I will talk about, I will extend my discussion on charged black holes and talk about how we can extend the Reissner-Nordström metric within the event horizons. So the outline of this lecture is as follows. First, as always, I'm going to talk about what we did in the last lecture. Then I'm going to talk about the coordinate singularities in the Reissner-Nordström metric. Afterwards, I'm going to show how we get rid of these coordinate singularities using null coordinates. And then I will show you how to draw Eddington-Finkelstein diagrams and show you the causal structure of Reissner-Nordstrom spacetime. Subsequently, I will talk about event horizons in the Reissner-Nordstrom metric and show you the behavior of the time and space axes once we cross the event horizons. And afterwards, I will give a brief discussion on the curvature singularities in Reissner-Nordstrom spacetime. So recall, in the last lecture, we proved the generalized Birkhoff's theorem, which states that a spherically symmetric solution to the vacuum Einstein field equation with a radial electric field is static and asymptotically flat. And we've shown the converse of this using black hole uniqueness theorems. So we have not shown it, but I've stated that you can show it using black hole uniqueness theorems. So to derive this result, we solve the Einstein-Maxwell equations, which is as follows. And we do this for a spherically symmetric metric and a radial electric field. So recall that a spherically symmetric metric is written as follows, and we've shown how to do this using coordinate transformations in lecture 1. And by solving the Einstein-Maxwell equations, we find that B dot is equal to 0, where the over dot is the derivative with respect to coordinate time. And this being 0 implies that B is completely time independent. And we showed that by virtue, this means that A is also completely time independent. So by solving the Einstein-Maxwell equations, we find that B takes the following generalized form and A takes the following generalized form. So these are the general solutions to the vacuum Einstein-Maxwell equations for a spherically symmetric metric. And this, for now, completes the proof of the generalized Birkhoff's theorem. So basically, we've shown that both A and B are time independent, which implies that they are static. And we've shown that they are asymptotically flat, because if we set R to infinity, B and A do not diverge. In fact, they converge to a constant. So this means that they are asymptotically flat. However, in order to derive the Reissner-Nordstrom metric, we have to use a boundary condition. And the Reissner-Nordstrom metric is simply a specific solution to the generalized, the generalized equation. So we use the argument that if Q is equal to 0, then the metric for a charged black hole should reduce to the Schwarzschild metric. And as a result, we find that C1 must be equal to 1, and C2 must be equal to minus 2m. And from this, we derive the well-known Reissner-Nordstrom metric. So now let us talk about coordinate singularities. So in lecture 1, we have already discussed 2 kinds of singularities, namely the coordinate singularity and the curvature singularity. So let's go back to this equation. We can see that here r equals 0 is obviously a singularity, because here, if r equals 0, this diverges, but it's in the denominator, so this could be 0, but this one, the time component still diverges. So, however, with the benefit of hindsight, we know that this is a curvature singularity. So as a reminder, if you forgot what the difference between a coordinate and a curvature singularity is a coordinate singularity is one that can be removed by coordinate transformations. And this means that if something is unphysical in a particular reference frame, it is just a matter of, it is just a problem with that reference frame, because the whole point of general relativity is that physics is essentially observer relative. And by changing the coordinate, so basically changing the coordinates that you use, you change the observer, the reference frame of the observer. So by doing this, basically something that may seem unphysical in one reference frame may be completely physical in another reference frame. So this doesn't mean that it is unphysical at all. However, a curvature singularity is a singularity that cannot be removed by coordinate transformations. This means that it remains unphysical in every single reference frame. So this is basically something that it is in fact unphysical. So basically, with the benefit of hindsight, we know that r equals 0 is a curvature singularity. And we will explain why this is the case in subsequent slides. But we have done this for the Schwarzschild metric. So, and the argument is essentially identical. So if you should, in principle, already know how to do it. But nevertheless, I will show you how to do it. For now, let us look at the coordinate singularities. So another not so obvious coordinate singularity is basically here. So when this the denominator here is equal to 0, because the r term will diverge. So it is not, I guess, trivial to see that this is a coordinate singularity, but nevertheless, we know, well, from experience, we know that this is a coordinate singularity, and I will show you how to remove them in subsequent slides. So we have to solve this equation for r. So by multiplying r squared on both sides, we obtain a quadratic equation. And generally, quadratic equations are very, very easy to solve. They have a generalized analytic solution, and so you can solve them using the quadratic formula, factorization, or completing the square. So using the quadratic formula, this equation can be solved. So R has the following solutions. So we can see that if Q tends to 0, this corresponds to a root at R equals 0 and R equals 2m, which is exactly the Schwarzschild case. And hence we can infer that these coordinate singularities correspond to the event horizons. And from this, we can find that there are 3 interesting cases. So the first one is that when m is greater than the absolute value of Q, in other words, this means that the discriminant is positive. So what this means is that there are 2 distinct roots, and hence this implies that there are 2 event horizons, which is very interesting, because what happens is in the Schwarzschild case, we know that there is only 1 event horizon. So by adding a charge component, we can see that there can be extra event horizons. Another interesting case is when m is equal to the absolute value of Q. So this means that the discriminant is 0, and hence there's only 1 distinct real root, or 1 degenerate root. So this means that there is only 1 event horizon, but notice that this event horizon is not at r equals 2m, it is at r equals m. So by adding a charge component that is equal to the magnitude of the mass of the black hole, we have an event horizon that is reduced. So this is an extremely important class of black holes called extremal black holes. And we will discuss it later in maybe 2 or 3 lectures time. But what is interesting about this solution is that it has connections to things like supergravity and string theory. So extremal black holes are really interesting because what happens in this case, you can make the Einstein-Maxwell equations linear and superpose multiple black holes over each other. And this is known as the Majumdar-Papapetra solution. And additionally, this has connections to things like positive energy theorems and spinor gravity, which is quite nice. So this is a very interesting class of black holes. The final case is that when m is less than the magnitude of Q, This means that the discriminant is less than 0, and there are two distinct complex roots that are complex conjugates of each other. And since we are not dealing with complex manifolds, this means that there are no event horizon. And this is a big problem, because in general relativity, there is a conjecture that we always assume, because a lot of results in black hole physics are dependent on this conjecture. It is called the weak cosmic censorship conjecture. And formally, it states that no curvature singularity can be seen from future null infinity. In other words, it means that a curvature singularity must always be hidden behind an event horizon. And since in the two complex root cases, there are no event horizons, this means that there is an exposed singularity that can be viewed from future null infinity, which means that, well, we call this a naked singularity. And the general assumption is that general relativity forbids this. However, the weak cosmic censorship conjecture is a conjecture for a reason. It has not been rigorously proven. It is just assumed. And it is one of the biggest problems in mathematical physics and the theory behind general relativity. But I hope, fingers crossed, that it is correct, because otherwise, maybe the past 50 or 100 years of black hole physics will be wrong. So now, let us talk about null coordinates. So like in the Schwarzschild case, we can add an advanced time, which is t with some arbitrary function of r, or some retarded time where t is subtracted by some arbitrary function of r. And to save writing, let us write v as equal to 1 minus 2m over r plus q squared over r squared, which is essentially the GTT component of the metric. And let us write the angular components as d omega squared sub 2. So this is the angular components of a 2-sphere. So by substituting dt in terms of du and dr in the Reissner-Nordström metric, we yield the following equation. So this is essentially the Reissner-Nordström metric in UR theta phi coordinates. And from the equation above, we can see that the coordinate singularity at r equals m plus or minus square root of m squared minus q squared is completely encoded in the dr squared coefficient. And one simple way to remove the coordinate singularity is to set this coefficient to 0. And doing so, we yield the following differential equation, where we have f prime of r is equal to r squared over this quadratic, and we can write this as r minus r plus, r minus r minus, where r plus or minus are the roots of the quadratic equation. And to solve this, we simply integrate both sides with respect to r. And if you don't know how to do this, this is very simple. You can do it in two ways. You can either factorize. So basically, this is an r squared term, there's an r squared term. You can do it by factorization, or you can simply use partial fractions and separate them as addition. So because doing integrals of r and 1 over r are quite easy if you separate them as addition. So what happens is you get doing this integral, you find the following formula, which is quite ugly, and I don't expect you to remember it, but we can see that this is done by partial fractions, because we have a natural log r minus r plus and natural log r minus r minus. So this is quite a nice, to me, I think this is quite easy to remember, but to some it may not be. So therefore, the Reissner-Nordström metric in null coordinates can be written as follows. So we have this term here, and we have du dv plus r squared times the angular coordinates. So now, to look at the causal structure of Reissner-Nordström black holes, we have to inspect the radial null geodesics. And to do so, we simply suppress the angular coordinates to obtain the null geodesics. So by doing so, we set ds squared equal to 0 to obtain the null geodesics, and then the metric in null coordinates is as follows. And hence, the obvious solutions are du equals 0 and dv equals 0, which implies that t minus f of r is equal to some constant, and t plus f of r is equal to some constant. So before proceeding, let us examine the function f of r. So if we look at the region, so basically these spikes here corresponds to the asymptotes at r minus and r plus. So basically, since we know that r minus must be smaller than r plus, because because we ruled out complex roots in the discriminant, and so basically what happens is the discriminant must be positive, and the square root of a positive number is always positive or negative. So so basically, if we take the negative root, we get something smaller. So we know that r minus must be smaller than r plus. So here, this asymptote corresponds to r minus, and this asymptote corresponds to r plus. So we can see in the region that we have three different regions, basically. So basically, for r less than r minus, we can see that t. So basically, this is r, right? So basically, in the region r less than r minus, f of r is greater than 0. Here, r between r minus and r plus, it is initially greater than 0, but eventually it hits the r-axis and it starts asymptotically approaching minus infinity. Then in the region r greater than r plus, it starts becoming it starts off negative, but eventually becomes positive. So recall that du is equal to corresponds to the solution. So sorry, du equals 0 corresponds to the solution t minus f of r equals some constant. So since f of r is increasing with r in the region r less than r minus and r greater than r plus, this means that t is also increasing in these regions. This is because we have some constant, so this constant can be positive or negative, it doesn't really matter. But if we add both sides, so this we have t equals something plus f of r. So basically t must increase with f of r. So on the other hand, since f is decreasing in the region r minus, it is decreasing in the region r between r minus and r plus, then t is also decreasing in this region. On the other hand, the solution dv equals 0 corresponds to the completely opposite relation, since there is a opposite sign on the f of r. So if we move it to this side, we have minus f of r, and the sign is flipped. So this means that in the regions r less than r minus and r greater than r plus, this means that t is decreasing, whereas in the region r between r minus and r plus, this means t is increasing. And what does this mean? This means that this coordinate corresponds to outgoing null geodesics, and this one corresponds to ingoing null geodesics. So what does that mean? So this Finkelstein diagram corresponds to u equals constant. And the reason why we call it outgoing null geodesics, it's because the light cones are pointing out of the black hole. So basically, let me explain what's going on. So these lines, the blue lines, correspond to lines of u equals constant. And the red lines correspond to the lines of u minus r equals constant. So what happens is a light cone is defined by the intersection between the blue, so basically a circle. So let's draw a circle like this between the intersection of the blue and red lines. So we can see what happens when the light cone goes towards these two black lines. So this black line represents the coordinate singularity at r minus, and this black line corresponds to the coordinate singularity at r plus. So if we focus on one of these light cones, right? Let's draw a circle here. So as light cones move towards the singularity, see it gets tipped So the light cones get tipped more towards the black line until so basically the future light cone is completely tipped towards the singularity. So basically, this light cone is basically inside the singularity. So what happens is if we continue, we can see this pattern occurs and keeps getting tipped. But what happens is when we cross this boundary, this light cone is completely tipped outwards. But notice that this is pointing out of the black hole. So this is why we call it outgoing null geodesics, because the light cones are not getting tipped in towards the black hole like in the short-lived case, but it's getting tipped outside, not in short-lived, sorry, in the ingoing case where the light cones are escaping the black hole. And this is actually not a black hole. This is what we call a white hole, because what happens is black holes are things that so basically light cannot escape from black holes once they cross the event horizons. But on the other hand, for a white hole, nothing can enter a white hole. So white hole is essentially emitting light. So this is the solution for a white hole. So it is the light cones are getting tipped outside the black hole. But what do we find interesting about ingoing null geodesics? We have the completely opposite relation. So what happens is so basically outgoing null geodesics is basically if we put a negative sign in front of every term here, so negative here, so we obtain the inverted Finkelstein diagram. So what happens is if we draw light cones here, so we draw a light cone here, what happens is we see that we have a similar behavior, that the light cone is getting tipped towards the singularity. You see here? So the light cones get tipped towards, and once it crosses the second one, it's getting tipped more and more towards the curvature singularity at r equals 0. But notice here, in this diagram, the light cones are being tipped in this direction. So basically pointing here, this direction. But in this case, the light cones are being tipped in this direction. This means that the light cones, the light cones are being tipped towards the black hole. So this actually corresponds to a black hole solution. So basically, light cannot escape from a black hole. The reason for this is because once a light cone has crossed the event horizon, your future is completely trapped inside the region of the black hole, whereas your past is outside the event horizon of a black hole. And the only way that you can escape a black hole is that if you can invert this this light cone. And what happens is then you would have to invoke things like time travel, which is essentially not really physical in general relativity. But what is interesting is with using null coordinates, you get two different solutions. One corresponding to white holes, where the light cones get tipped out away from the black hole, the event horizon of the black hole. But one where light cones are tipped towards whereas the other one is tipped towards the event horizons of the black hole. So this is quite an interesting property of null coordinates. So then what we will find interesting is what happens if we plot u and v on the same graph, and we can see a very similar behavior where the light cones still get tipped. So basically, if you choose if you have this red line and this blue line here, and you draw a light cone here, if you point in this direction, we can see that the light cones get completely tipped towards the singularity from one point of view. But if we draw the light cones in this manner, so we draw this as the light cone, they get tipped outwards. So you can see simultaneously that we have one solution corresponding to light cones being tipped towards the singularity, and one where the light cones are being tipped away from the singularity. So this diagram is actually very, very nice because it's one of my favorite diagrams in general relativity by plotting the null coordinates together. Now that we have discussed Finkelstein diagrams, let us discuss properties of the event horizon. So we have already discussed in the lecture on Eddington-Finkelstein coordinates, the properties of event horizons. And eventually we will define the event horizon more rigorously when we discuss Cauchy problems in general relativity, when we discuss asymptotic flatness, and ultimately singularity theorems. But let us examine what happens to the t and r axes when a particle is in the regions r less than r minus, r between r minus and r plus, and r greater than r plus. So let us write the Reissner-Nordstrom metric as follows, where GTT is equal to 1 minus 2m over r plus q squared over r squared, and GRR is simply 1, the reciprocal of GTT. And we write this as the angular coordinates of a two-sphere. So for pedagogical purposes, let us graph GTT and see the behavior of the particle once it crosses the horizons. So we can see GTT, and we can see what happens when the particle basically crosses the horizon. So basically when r is very, very small, it is GTT is greater than 0. And when it passes, so basically it's positive, right? But when it passes r minus, it becomes negative. And then eventually there is a local minima. And what happens is when we proceed to increase r at r equals r plus, it will become positive again. So there is a turning point between these two roots, I guess. So what does this mean? To summarize, in the region r less than r plus, GTT is greater than 0 and GRR is greater than 0. In the region r between r minus and r plus, GTT is less than 0 and GRR is also less than 0. And in the region that r is less than r minus, GTT is greater than 0 and GRR is also greater than 0. So I guess so you're asking, so what? So recall that in Minkowski spacetime, the time signature is always negative and the spatial signature is always positive. So they share opposite signs. So what happens is when we cross so in the regions r plus and r minus, what happens is the metric signature remains unchanged. But when we reach the region r between r minus and r plus, the metric signatures change. So the GTT component becomes positive and the GRR component becomes negative. And one principle in relativity is that we treat time and space on equal footing. So therefore, we can see that in the regions r greater than r plus and r less than r minus, the time and space coordinates behave normally. However, in the region r between r minus and r plus, the time and space coordinates are inverted. So basically, in the region between the two event horizons, the time and space coordinates are flipped. So your time will become your space coordinate and your space will become your time coordinate. So if you were an observer going into the black hole, this would seem very, very trippy. But in the regions r greater than r plus and r less than r minus, basically you would see everything as normal. Now, now let us talk about the boundary of the event horizon and what the area of the event horizon is. So recall that at some constant time t, dt equals 0. So the surface of the event horizon of a short-filled black hole is described by the following formula. So basically, this is essentially the first fundamental form. And what we can do is integrate over the surface of a sphere to yield the area. So to get the first fundamental form generally is that we integrate over the coordinates, integrate the determinant, the square root of the determinant of the first fundamental form over the coordinates. So integrating over the surface of a sphere yields the area of the event horizon. So this is for a short-filled black hole. So we can simply alter the formula to obtain the formula for a Reissner-Nordstrom black hole. So what we do is we simply replace this RS with the roots of the equation we simply replace 2m with the roots of the equation for the coordinate singularity, so namely r plus and r minus. So by altering the formula, we get the area of the inner and outer event horizon. So we simply say 4 pi. We multiply 4 pi by r plus or minus squared, and we get the following formula. So we get 4 pi times m plus or minus a square root of m squared minus q squared. And we can do some interesting things. We can just set q to 0, and we can see that this corresponds to, so if q is equals 0, we get m squared here. So square root of m squared is simply m. So we get plus or minus. So if we get minus, we get an event horizon with an area of 0. And we've already shown that this is not possible by the weak cosmic censorship conjecture, as this would expose a naked singularity. So we neglect the negative root. And if we have the positive root, we have square root of m squared is just m plus m is 2m. 2m squared is 4m squared, sorry. So basically m squared square root plus m is 2m. 2m squared is essentially 4m squared, and 4 times 4 is 16. So we get 16 pi m squared. So by setting q equals to 0, we get the Schwarzschild case. So this formula seems valid. And what's interesting is if we get extremal black holes, we get something even more interesting. So if m is equal to q, this is essentially 0. And what happens is we get 4 pi m squared. So we get a reduced area for extremal black holes, which we will discuss in 2 or 3 lectures time. So now let us talk about curvature singularities. And recall from a couple slides back, there seems to be a curvature singularity at r equals 0. And to prove that this is indeed a curvature singularity, one can compute an invariant known as the Kretschmann scalar, which is defined by the Riemann tensor contracted with itself. And we obtain this very, very complicated expression, right? And the computation of this Kretschmann scalar is extremely tedious. And when I calculated it, I used Mathematica to do it, basically some algebra handling language. And you would never want to do this by hand, just to say. But we can see that the key message here is that the Kretschmann scalar diverges at r to 0. And since scalars are coordinate independent, the singularity at r equals 0 diverges in all charts. This means that there exist no charts for which the metric can be smoothly extended through r equals 0. So basically, in other words, what this means is basically vectors and tensors are coordinate dependent. But in this case, we have a scalar, and scalars are not dependent on the coordinates. So basically, they're coordinate independent. And by doing this, by showing that there exists a singularity in a scalar quantity, this shows that no matter what's reference frame you choose, this singularity will exist. And we will discuss the definition and conditions for curvature singularities in future lectures when we discuss Penrose's incompleteness theorem. But that will be some lectures away. I will have to derive the Null Reissner-Nordström equation. I will have to define things like global hyperbolicity. I will have to define null energy conditions and compact trap surfaces, which are very, very complicated. But we will be able to do them in some lectures time. That is basically it for this lecture. And in the next lecture, I will try to extend the Eddington-Finkelstein coordinates, basically maximally extend the Eddington-Finkelstein coordinates to draw Penrose diagrams. And the reason for this is because there seems to be some disconnect between the advanced or time solution and the retarded time solution. And this is basically there seems to be no connection between the two black hole and white hole solutions. So to maximally extend them, we draw a connection between these two solutions. So that will be when we discuss Kruskal-Szekeres coordinates for Reissner-Nordstrom metric. And in the future, I plan to also do a video on geodesics for Reissner-Nordstrom metrics, and I will do this using Mathematica. So basically, it is a more code-heavy video, and I think some of you will like that a little bit more because I can show some graphs and some qualitative analysis. So I hope you've learned something in this lecture, and I'll see you in the next one. Thank you.